Welcome back to the deep dive. Just take a second to think about your own vision. It's
Yes.
well, it's pretty incredible, isn't it?
It really is something we take for granted most of the time.
Totally. Like how you walk from bright sunlight into a dim room and your eyes they just figure it out almost
hmm
instantly.
Or how you can spot a friend in a crowded place or, track a bird flying across the sky.
Effortlessly.
Exactly.
Yeah.
It's an absolutely astounding piece of biological engineering. But, okay, what if we could do more than just understand how it works? What if we could actually recreate it?
That's the big dream, isn't it?
Yeah, not just, for science's sake, but maybe to help people who've lost their sight.
Yeah.
Or even give machines, I don't know, human-like vision.
That's precisely the challenge and the real driving force behind a lot of cutting-edge research right now. Neuroscience, bioengineering, AI, they're all converging on this.
Because our biological system is just,
Yeah.
it's so good, so adaptable, so efficient. Unparalleled, really. The way it processes information, handles complexity, uses so little power, nothing we've built quite matches it yet.
Right. And that's exactly what we're diving into today. A really big leap forward in trying to build something like it. A neuromorphic digital retina. They've actually emulated it on an FPGA.
Neuromorphic.
That's the key word there.
Yeah, for anyone maybe not familiar, neuromorphic basically means brain mimicking. So in this case, it's designed to copy the structure, the function of our actual biological retina, how the neurons work, how they talk to each other.
It's about building silicon that tries to act like biology.
So it's not just a camera sensor taking pictures.
Not at all. That's the old way, sort of passive recording of pixels. Neuromorphic systems. They process information right there at the sensor level, like the brain does, or like the retina does in this case, trying to pull out the important stuff immediately.
Okay, so our mission for this deep dive is to unpack a specific scientific paper. It's by Prince Philip and his team.
A really fascinating piece of work. Totally. They've built this digital retina that actually shows some key biological tricks that have been, well, super hard to copy artificially before now. So think of us as your guide. We'll try to cut through the complexity, find those aha moments, maybe some surprising bits.
You get you to the core ideas without drowning in the jargon.
Exactly. And you'll see how this thing can adapt to light, how it spots movement and edges, processes information really efficiently, kind of like our own eyes do.
And this isn't just theory. It's a real step towards things like better visual prosthetics, smarter robots. It's tangible.
Okay, but before we get into the digital version, we really need to understand the original blueprint, right? Our own biological retina. Let's start there. What's its basic job?
It's absolutely fundamental. The retina sits at the back of your eye, and it's the very first place where light gets captured and turned into electrical signals.
The first step in seeing anything.
The very first step. But it's not just catching light like film in an old camera. It's immediately starting to process it. Light hits the photoreceptors, the rods and cones.
Right, rods for dim light, cones for color. School biology.
Exactly. They convert that light energy into an electrical signal. But then that signal doesn't just shoot straight to the brain.
No.
No, it gets passed through this whole network of other neurons right there in the retina.
Huh.
Bipolar cells, horizontal cells, amacrine cells. It's a whole processing layer cake.
Wow, okay. All happening inside the eye itself.
And all that interaction, that processing, refines the signal and eventually generates what we call action potentials,
Nerve
impulses.
Ah, the actual language the brain understands. The electrical spikes.
Precisely. These spikes, kind of like digital bits on or off, travel down the optic nerve.
Which is like the big data cable connecting the eye to the brain.
You got it.
Yeah.
It carries this already pre-processed information to a relay station deep in the brain called the lateral geniculate nucleus, the LGN. Which is part of the thalamus. From the LGN, it goes to the primary visual cortex, V1, at the back of your head. And even then, it's not done. It gets sent on to higher visual areas for more complex stuff like recognizing faces or understanding a whole scene.
So it's a whole cascade, definitely not just eye sees, brain gets picture. The retina is doing some serious work up front.
A lot of work.
Yeah.
It's doing complex initial processing, things like calculating brightness, detecting motion, and crucially, finding edges.
Edges. Yeah, that seems fundamental. That's how we separate objects from backgrounds, right?
Absolutely critical. Without good edge detection, the world would just be a confusing smear. And the paper really emphasizes this. Getting that mapping right from the light coming in to the neural signals going out is vital for clear vision.
Makes sense. If the first step is wrong, everything downstream is going to be off.
Exactly. Garbage in, garbage out, Even applies to biology.
Okay, so the retina's got these hidden smarts. What are the really sophisticated biological tricks that this new digital model is trying to copy? The stuff that's been hard to do before.
All right, this is where it gets really interesting.
Hmm.
One of the biggest ones is center surround receptive fields, RFs.
Center surround rings a bell, like a target shape.
Kind of, yeah. Imagine a tiny spot on your retina. A neuron looking at that spot has a receptive field. In a center surround setup, the middle part might get excited by light while the ring around it gets inhibited. Or the other way around, inhibited center, excited surround.
So light hitting the middle does one thing, light hitting the outer ring does the opposite.
Exactly. And that structure is the basis for something called lateral inhibition.
Lateral inhibition.
Yeah, it basically means that activity in one area suppresses activity in the neighboring areas.
Yeah.
And the effect, it dramatically sharpens our perception of edges and contrast.
Ah, so it makes boundaries stand out more clearly?
Precisely. It makes the edges pop. It helps you pick out objects even against a really busy background. It's like built-in contrast enhancement happening right at the start. Very clever.
That is clever. Okay, what else? What other biological marvels are they tackling?
Another huge one is luminance adaptation. This is that thing you mentioned earlier, walking from sunshine into a dim room.
Yeah, how our eyes adjust so quickly.
Amazingly quickly. Our eyes can handle an absolutely staggering range of light levels. The paper says over 10 orders of magnitude of illumination.
10 orders of magnitude. That's astronomical.
Maybe, yeah.
Billions of times difference in brightness.
It's immense. Way, way beyond any standard digital camera sensor. And the challenge for the retina is to somehow squeeze all that information, that huge range, into the relatively tiny bandwidth of the optic nerve fibers.
Which can only fire so fast, right? A few hundred spikes per second.
Exactly. So it has to compress that enormous input range without losing the important details. It's constantly adjusting its sensitivity, like an automatic volume control for light.
Incredible. Okay, so adapting to overall brightness. What about variations within a scene?
That brings us to contrast gain control. This is a bit more subtle, but really important. The retina adjusts its sensitivity based on the average contrast in the scene you're looking at.
So not just how bright it is overall, but how much difference there is between the light and dark parts within the scene.
Exactly. If you're looking at something with very low contrast, like subtle shades of gray, the retina actually boosts its sensitivity to help you see those differences. If it's a really high contrast scene, it dials back the sensitivity a bit to avoid getting overwhelmed or saturated.
Huh. So it's always trying to optimize for the current conditions to keep details visible?
Precisely. It preserves your perceptual sensitivity, makes sure you're getting the most useful information, enhancing features. It's another layer of smart automatic adjustment.
Okay, and then there were those two cell types, phasic and tonic. What did they do?
Right, these show the dynamic side of retinal processing. Phasic cells are the change detectors. They give a transient response.
Transient, meaning brief.
Yeah, they fire a quick burst when something changes, when a light turns on or off or something moves, and then they quiet down pretty fast. Think about how motion in the corner of your eye catches your attention instantly. That's likely phasic cells doing their job.
Like little alarm bells for novelty?
Exactly. Really good for locating an object in a cluttered visual scene, as the paper puts it. Then you have tonic cells. They give a sustained response.
Sustained, so they keep firing.
Right. As long as the stimulus is there, they keep sending a signal. They maintain a consistent representation. These are useful for things like tracking moving objects once you've already noticed them, giving you that continuous perception.
So phasic for the, hey, something happened, and tonic for, okay, I'm still seeing it.
That's a great way to put it, yeah. They work together to give us this rich, dynamic view of the world. And these features center surround, luminance adaptation, contrast gain, phasic-tonic responses. These are the things that have been really tough to get right in artificial systems.
Okay, that makes sense. That biological complexity is just immense. So let's shift to the engineering side. People have tried to build digital retinas before, right? What did those earlier attempts look like? And critically, why didn't they quite nail it?
Oh, absolutely. There's been a lot of important groundwork laid over the years. Researchers built various hardware models, some on FPGAs like this one, some using specialized processors. There were studies looking just at spiking patterns, lots of building blocks.
So people were definitely working on it.
For sure. There were digital cellular neural network models of the outer retina, hardware platforms designed for quick testing, early demonstrations that could produce some ganglion cell-like responses.
Yeah.
All vital steps.
There were still gaps. What was missing from those earlier digital copies?
The main issue was that, despite the progress, these earlier models often struggled to capture that whole package of sophisticated biological features we just went through.
Ah.
So maybe a model did okay with edge detection, but didn't have luminance adaptation. Or it might have had some adaptation but lacked realistic center surround fields. And getting that dynamic contrast gain control right was a big hurdle. Plus, mimicking both phasic and tonic cells reliably in one system was often missing.
So they might have captured parts of the puzzle, but not the whole integrated picture. Like they didn't have all those hidden smarts working together.
Exactly. The consequence was, as the paper says, they didn't generate an output that is close to the biological retina. They weren't biologically realistic enough in their overall behavior.
And why is that realism so important? You mentioned it's an imperative task, especially for things like prosthetics.
Because if you're building, say, an artificial eye for someone, you don't just want to give them any visual signal. You want to give them something their brain can actually understand, something that feels natural, something useful.
Right, not just random flashing lights.
Precisely.
Yeah.
The closer the artificial system mimics how our own retina processes information, how it adapts, finds edges, detects motion automatically, the more intuitive and effective it will be for the user. It moves it from just sensing light to actually helping someone see and navigate their world.
That really puts it into perspective. Okay, so that brings us to this breakthrough by Prince Philip's team. What's genuinely new here? What are the key innovations that finally managed to bridge those gaps?
Well, first, they built upon an existing model called the Convex retina model, but they significantly extended it. They introduced several key innovations that directly tackled those missing pieces we just discussed.
Okay, let's get into those innovations. The first one sounds pretty technical. A non-separable spatiotemporal OPL filter. What does non-separable mean here, and why is it a big deal?
Right, non-separable means that the processing of space, where things are, and time, when things change, in that first layer, the outer plexiform layer, or OPL, are intertwined. They're handled together, not as separate steps.
Unlike simpler filters that might do spatial stuff first, then temporal stuff.
Exactly. Biology often doesn't separate them cleanly like that. And the power of this non-separable approach is that it can effectively detect changes in brightness, even if the scene is totally uniform spatially.
Huh. How does that work if nothing's changing in space?
Imagine looking at a perfectly blank wall, but the overall room lighting slowly dims or brightens. There are no edges or patterns changing, only the overall light level changing over time. A simpler, separable filter might struggle with that because it relies heavily on spatial differences, but this non-separable filter can pick up on that purely temporal change.
Ah, okay. So it's more sensitive to subtle overall changes, just like our eyes are. That's clever. What's the next innovation?
The next one is incorporating a biologically plausible delay in the surround signal. Remember the center surround receptive fields?
Yeah, the bullseye pattern.
Well, in our actual retinas, the signal from that outer surround part is slightly delayed compared to the signal from the center part. It doesn't arrive at the processing neuron at exactly the same time.
A tiny delay. Seems like a small detail.
It seems small, but biology is efficient. This model includes that specific delay. And here's the aha moment. The way they implemented this OPL layer using what's called a difference of Gaussian for space and a biphasic filter for time, plus that delay, it allows this single layer to act as both an edge detector and a movement detector.
Wow. Okay, so that one layer is pulling double duty because of that specific timing.
Exactly. The spatial difference helps find edges, and the temporal difference, emphasized by that delay, helps detect motion. It's incredibly efficient, just like biology tends to be.
Nature's optimization at work. Okay, how do they crack the luminance adaptation nut, handling those massive swings in brightness?
They integrated luminance adaptation via high-pass filtering right at the start at the photoreceptor level.
High-pass filter, that tends to emphasize changes, right?
Precisely.
Yeah.
By applying it right where light is captured, it effectively filters out the slow, steady background brightness level and lets the changes, the details within the scene, pass through more strongly. It's like automatically adjusting the baseline so you can focus on what's actually happening.
So that directly tackles that huge dynamic range problem we talked about. Makes sense. What about the contrast gain control? Adjusting sensitivity to the scene's contrast.
For that, they implemented nonlinear contrast gain control. The key here is nonlinear. It's not just scaling the signal up or down linearly. It models the complex, distinctive nonlinear dependency that biological retinas show, where the adjustment depends intricately on the average contrast level.
So it's a much more sophisticated, nuanced adjustment than just turning a volume knob up or down.
Exactly. And it's designed to account for how contrast affects both the spatial and temporal processing simultaneously. This signal shaping happens not just in one place, but is also refined later in the inner plexiform layer, IPL. It's a system-wide adaptation.
Okay, and hitting those phasic and tonic cells, the change detectors and the presence detectors, that seemed like a big stumbling block for older models.
This is one of the most elegant parts, actually. They found they could achieve both types of responses simply by varying the strength of a partially high-pass filter.
Seriously, just by tweaking one filter setting.
Essentially, yes. By adjusting how strongly that filter emphasizes changes, they can make a cell respond briefly and sharply to changes, phasic, or respond more continuously as long as the stimulus is present, tonic.
Wow, that's incredibly efficient, getting that whole spectrum of responses from one simple adjustment.
It really is. It shows a deep understanding of the underlying mechanisms. And one last key feature. The whole design is reconfigurable.
Meaning you can change how it works after it's built.
Exactly. You can adjust parameters, maybe even change some of the connections or filter types on the FPGA. This is huge for research and development. It makes it crucial for testing or comparing other biological retinas, maybe from different animals, or for rapidly trying out new ideas for visual prosthetics.
So it's not just a fixed model, it's a flexible platform for future exploration.
Precisely. Makes it a really powerful tool.
Okay, this architecture sounds incredibly well thought out, layer by layer, mimicking the biology. How does it actually work in practice? Let's trace the signal flow, starting from light hitting the digital photoreceptors.
Right, so the model simulates that whole chain. Photoreceptors to ganglion cells, just like in the eye.
Starting with the outer plexiform layer, OPL, that first filter, what happens there digitally?
Okay, biologically, this is where photoreceptors meet horizontal cells and bipolar cells, and those crucial center surround fields get formed through lateral inhibition. Digitally, the input is luminance values, pixel by pixel. From video frames, they used 128 by 128 initially.
So raw brightness data goes in?
Yep. Then the OPL applies those spatial filters, the Gaussian ones, to mimic the receptive field shapes. And it applies temporal filters, low pass and high pass, to handle how the signal changes over time.
And the core calculation?
The core output, IOPL, is calculated as CS, the center signal minus the surround signal. That's the digital implementation of the center surround antagonism. That's what starts enhancing edges and contrast right away.
And you mentioned it's efficient.
Yeah, they use infinite impulse response, IIR filters, for the temporal part. It's a computationally cheap way to factor in past information, which is great for real-time processing on hardware. And remember, this layer is already acting as both an edge and a motion detector.
Very cool. Okay, moving on. Next up is bipolar level contrast gain control. How does this layer adjust the sensitivity digitally?
So biologically, this is where the retina starts adapting to the overall contrast level in the scene. Digitally, it takes the IOPL output from the previous layer.
Right.
It uses components called leaky integrators. Think of them like small buckets that slowly leak, so they respond more to steady or increasing input. There's also feedback involved, using something called a shunt conductance, GA. The key is a nonlinear function, Q, VBIP, that shapes the output based on the current signal level, PBIP.
That nonlinearity again seems important.
Crucial for biological realism. The output of this layer, VBIP, is a signal that's been adjusted, gain controlled, based on the input contrast. It's ready for the next stage.
Which is the inner plexiform layer, IPL, and the ganglion cells. This is where the spikes happen, right? The transition to the brain's language.
Exactly. Up to this point, the signals have been more like analog levels, graded potentials. But the retinal ganglion cells, RGCs, are the ones that fire those all-or-nothing spikes that travel down the optic nerve. This digital model simulates that critical step.
How does it prepare the signal for spiking? What's this excitatory current eye gang?
The IPL in a real eye is super complex, lots of synapses. This model simulates the signal shaping that happens there, mimicking different biological cell types like the primate paromagnocellular pathways. Digitally, it applies another temporal high-pass filter, TG, to emphasize changes, and another static nonlinearity function, NVBIP, to shape the signal further.
And this is where the on and off responses are determined.
Yes. There's a parameter. Set it to 1, you get on spikes firing when light increases. Set it to emitting 1, you get off F spikes firing when light decreases. It lets the model replicate those two fundamental response types.
Neat. Okay, so now you have this IgAN current. How does it turn into actual spikes? That's the leaky integrate and fire LIF neuron model.
Exactly. The LIF model is a standard way to simulate basic neuron firing. That IgAN current essentially charges up as simulated membrane potential, VM.
Like filling up a capacitor.
Pretty much, yeah. It integrates the input current over time, but it also leaks a bit, so it needs enough input to keep charging. When VEAM hits a certain threshold, spike, a digital pulse is generated, and immediately after, VEAM is reset to 0. That mimics the neuron's refractory period, where it can't fire again right away. This converts the continuous IgAN signal into those discrete spike trains the brain works with.
Wow. Okay, so that's the whole pathway, from light hitting the sensor to spikes coming out the other end, all modeled digitally. Now, how did they actually build this, put it onto silicon?
Right, the silicon reality. They took all those mathematical models and the pseudocode describing the steps and translated them into a VLSI architecture. Very large-scale integration, basically designing the circuit layout for a chip.
And what chip did they use?
They implemented it on an Arctic 7 FPGA. Specifically, the EXA7A75 TCSG 324 2L model. That's a field programmable gate array built on modern 28-nanometer tech.
And that's good because...
Because that tech node is known for low power consumption and high efficiency. Super important if you're thinking about practical applications like wearables or prosthetics where battery life and heat matter a lot.
Definitely. Okay, how much of the chip did this digital retina actually use? What was the resource utilization?
The numbers from their table show it used about 1720 slices, 720 lookup tables, LUTs, around 3,700 flip-flops, also 98.5 block RAMs and 76 DSPs.
Translating that for us non-FPGA experts.
It means it's actually pretty compact. For the complexity it's simulating, it uses a relatively small footprint on the chip. That speaks to a very efficient design.
Efficient and powerful, presumably. What about the performance? How fast does it run?
They got it running up to 83 megahertz. It has a throughput of 12,000 samples per second, and the latency, the delay from input to output is really low, just 413 clock cycles.
And in terms of image processing?
It can handle 128 by 128 pixel images at 200 frames per second, which is pretty fast.
But I thought you mentioned something even better.
Ah, yes. In their conclusion, they state it's actually capable of processing 512 by 512 pixel frames at that same 200 frames per second rate.
Whoa. That's a huge jump in resolution while keeping the speed. That's seriously impressive performance.
It really is. Shows the architecture scales very well.
What kind of design specifics help them achieve that performance? Any clever tricks?
Yeah, they use things like dual-port RAMs, which let you read and write data at the same time without conflicts. The whole design is heavily pipelined like an assembly line, so new results come out every clock cycle. And they used optimized register banks like 3x3 or 5x5 blocks, specifically for speeding up the spatial filtering calculations. Lots of smart hardware design choices.
Okay, so they built this complex, efficient, high-performance digital retina. How did they prove it actually works? That it really mimics the biology? Validation time.
Crucial step. They compared its output directly against a software simulation, a quantized version of the Convis Retina model implemented in MATLAB. That software model was their trusted baseline, their ground truth.
Makes sense. Compare the hardware to a known good simulation. What did they feed into it for testing?
They used a standard test signal called a chirp stimulus. It starts with an off-off on-off pulse, then has oscillations that sweep up in frequency and amplitude. It's designed specifically to test how a system responds to dynamic changes over time.
Like putting it through its paces with a complex signal. And visually, how did the outputs compare?
The visual proof in the paper, looking at the graphs like figure 8 and 10, is pretty convincing. You see the hardware output, red lines, tracking the software output, black lines, incredibly closely. For the OPL signal, the bipolar potential, the ganglion current, and both the on-N and off-F spikes.
Any specific features that jump out in those graphs?
You clearly see sharp peaks at pulse edges, showing the high-pass filters doing their job. You see rectification, where signals don't go below 0, just like real neurons. And figure 10 shows a nice progression of a video input being processed layer by layer. Looks very biologically plausible.
Okay, visually convincing. But did they quantify it? Put numbers on how close the match was?
Absolutely. Quantitative confirmation. They calculated the variance explained, basically, how much of the software model's behavior the hardware could replicate. They found the bipolar and ganglion cell stages were extremely accurate.
Even if the first layer, the OPL, had slight differences.
Yeah, they noted some tiny numerical discrepancies in the OPL due to filter approximations. But the crucial later stages, the ones generating the output, were spot on. The overall fidelity was very high.
And timing, was there any lag introduced into the hardware?
Critically, no. They did a cross-correlation analysis, which basically checks how well the signals line up in time. The peak was right at the zero time step, signifying zero timing difference. The hardware was reacting just as fast as the software model, hugely important for real-time use.
Fantastic. And did they explicitly show it could do the tonic and phasic responses?
Yes, that was another key validation. Figure 11 shows it clearly. The digital tonic cells give that continuous response as long as the stimulus is there.
Just like the biological ones.
And the digital phasic cells give that brief response only when the stimulus changes. So yes, it successfully demonstrated that full range of biological response types.
Okay, it passed the tests. How does it stack up against other attempts, the comparison with other models?
That's where it really shines. Table 8 in the paper lays it out. The big advantage of this work is that it implements that whole suite of key features: contrast adaptation, luminance adaptation, center surround receptive fields, both phasic and tonic cells, and both on and off ganglion cell types.
So it's got the complete package, whereas others maybe only had some of those pieces.
Exactly. Many previous models might have implemented one or two, but getting them all working together in one biologically plausible and efficient system is the real breakthrough here. These features are what let it handle the wide input range of the visual system so effectively.
And it does all this while being efficient with resources.
That's the other kicker, yes. It uses fewer hardware resources than many comparable models listed in their comparison table. More biologically complete and more efficient. That's a win-win.
Definitely sounds like a significant step forward. Okay, let's zoom out. A vision for tomorrow. What's the big picture impact? Where could this technology lead?
The most direct impact, and the primary motivation mentioned, is developing better biologically plausible retinal prostheses.
Artificial eyes for people with vision loss.
Exactly. This is a concrete step towards devices that don't just stimulate the retina randomly, but do it in a way that mimics natural processing. That could mean much clearer, more useful, more intuitive vision for users. Truly life-changing potential.
Absolutely. What about beyond prosthetics?
Oh, lots of possibilities. Think about robotics and autonomous systems. Giving robots or self-driving cars vision systems that adapt to light and contrast like ours do, that detect motion and edges more robustly, that could make them much safer and more capable in complex real-world environments.
Yeah, overcoming those limitations current machine vision faces.
Definitely. Also, image processing. Using these bio-inspired principles could lead to smarter ways to analyze images in security, science, you name it. And there's that fascinating loop back to neuroscience and medical treatments.
The two-way benefit you mentioned.
Right. First, the model itself provides valuable insights into the human retina. Neuroscientists can use it as a tool to test ideas about how our own eyes work. Second, it can provide realistic, bioplausible input for visual cortex therapies. If you're trying to develop treatments for the brain's vision centers, you need realistic input signals to test them with.
So it helps us understand our own biology better and potentially develop new treatments for visual disorders based on that understanding.
Exactly. And finally, don't forget that power of reconfigurability. Because it's on an FPGA, researchers can easily tweak it, test variations, compare different biological models. It speeds up the whole cycle of research and development.
It really sounds like a foundational technology with wide-ranging potential. Okay, let's try to wrap this up. We've gone from the wonder of our own vision, through the challenges of replicating it, to the innovations in this specific neuromorphic retina.
Yeah, covering its ability to adapt, detect changes, process information efficiently, all mimicking biology pretty closely.
The big takeaway, the aha moment for me, is that this isn't just about building better cameras. It's about building synthetic eyes that genuinely learn from nature's design, processing information intelligently right from the start.
It's a shift towards truly intelligent sensors, inspired by biology.
So the final provocative thought for you, our listener, as we keep decoding biological vision and translating it into silicon like this, how might our own understanding of perception change? And what completely new kinds of sight for us or for machines might be just around the corner?
It's definitely an exciting frontier, lots to think about.
Indeed. Well, that's all the time we have for this deep dive. Thanks so much for joining us.
My pleasure.
We look forward to exploring another fascinating topic with you next time.